Rani from National Center for Medium Range Weather Forecasting, Ministry of Earth Sciences, India. And I am also a member of the scientific steering group of ESMO WCRP. So today I am going to give an overview of renewable energy applications of reanalysis. In this talk, I am not going to cover all the renewable energy applications, but I try to comprehends the wind and solar renewables, that what are the applications of reanalysis in those renewable field. So the outline I just introduced like this: introduction, what is the importance of renewable energy sources, then what is the global share of power production from renewable sources, and what is the dependence of weather data, that is the power production and the weather, and what are the reanalysis data strengths and limitations. So this one we are discussing for the this week, that last 3 days we are discussing what are the strengths and limitations of reanalysis data for different applications, and how is reanalysis useful in renewable energy applications, particularly then which reanalysis we should go, use for the renewable energy, particularly the wind or solar, whether it is which is the best, global or the regional reanalysis, and what are the different challenges when we use the reanalysis products in the renewable energy field. So the introduction, as we all know, the energy mix of most countries across the world dominates by fossil fuels, and this has major implication in the global climate as well as in the human health. So to reduce the carbon dioxide emission and local air pollution, the world needs a rapidly shift towards a low carbon source of energy, that is the renewable energy sources. So the renewable energy comes from natural sources or processes that are constantly replenished. So renewable energy sources are growing quickly and will play a vital role in tackling climate change, especially decarbonizing our energy systems. And what are the renewable energy sources? When we talk about the renewable energy sources, there are a lot of renewable energy sources. To list a few: hydropower, wind, solar, biomass, geothermal, then wave, tidal, and ocean thermal potential. All those are coming in the renewable energy sources. So before going into the renewable energy applications of reanalysis, where we stand, this is the global share of power production from renewables. So this I took from this particular site, Our World Data. So this is the site. So you can go and see what is, means they have given the comprehensive plots and data of all the renewable energy sources, the share of electricity production from renewable sources from 1965 to 2023. So this is the latest one. This is for 2023, and if you see, most of the countries, their renewable energy production, their electricity production share is coming from the renewable sources. That is mostly many countries, they have shifted to the renewable sources. More than 70%. If you see some countries over the South America, South Africa, then parts of US, then Europe, and some parts of Asia also. So the tendency is that all are moving towards the renewable sources for the electricity production. And if you see the modern renewable energy generation by source over the world, so still the hydropower is the first one. So this is in terawatt hours. So if you see, this is from 1965 to 2023. So the maximum the renewable share is coming from the hydropower, and the next is the wind, then solar, then the combined from other renewable, including the bioenergy. So if you see that in the recent years, recent past years, there is a decrease in the hydropower, but we can see there is an increase, steep increase in the energy production from wind and solar renewables, and from other renewable, including the bioenergy also. So then this is the share of electricity production from renewables on different countries. That is, this is just I took some different countries like Brazil, Sweden, China. Then this is coming the world also. So if you see that around 20% of renewable energy share, if we consider the world as a whole, it is also coming from the renewables. And France, United States, and I just put India also. So then if we talk about the power production, what is the dependence on weather data? So as we know, weather is modulating the power production and the transmission. So this relationship is growing stronger with the increase of weather-driven renewable generation. So with the rising levels of wind and solar generation, supply-side weather dependency is increasing rapidly. So if you see, the wind power output is very sensitive to small changes in wind conditions, because the wind power density is proportional to third power of wind speed. And solar power generation is sensitive to irradiance. And both wind and solar generations are impacted by temperature, humidity, and precipitation. And if we see, solar and to a lesser extent wind generation also affected by smoke and other atmospheric aerosol loads. So if we see what is the electricity and weather system dependence, so this is the picture I took from this particular reference, Energy System Integration Group 2023 Weather Dataset Needs Planning and Analyzing Modern Power System. So this picture comprehends the complicated relationship between the weather and the electricity system. So here different arrows shows the different connections. So here if you see the gray arrow, it shows the environmental variables are interdependent, but there is some strong internal links also. So if we see the aerosol and clouds, they are strongly dependent on the, so the incoming solar radiation, there is a strong dependence. And similarly, the precipitation, groundwater and snow and temperature, again it depend. So there are so many weather variables that has strong internal links. And the blue arrow, dependence of the electricity system on the climate system. So if you see the solar generation, then the load, the temperature, again depending on the grid stability, and again the wind. So this is the climate system impact. And the light blue color length, strength of dependence is highly variable and depends on asset type and location. So that is mainly for the hydroelectric power, that depends on the asset type and location and all. And this orange line, it shows the degree of dependence can be greatly amplified by specific weather and climatic condition. So there, as the weather and climate changes, it depends on the dependency is increasing. So basically, if you see the temperature increases, the solar wind generation, that also affects. Similarly, the precipitation, then the wind, then all those things are interrelated. So this is the complicated or the strong interrelation between the energy system and the weather system. So then we talk about the reanalysis also. From the reanalysis also, we are getting almost all these variables. So there is a strong interrelation between the energy production and the reanalysis variables from that. So then why the reanalysis data set, what are the strengths and limitations? So this we were discussing last 3 days, and we will be continuously discussing this one. So but one important component of the reanalysis framework, which is varying the source of raw input data. So this is unavoidable due to the ever-changing increase in the observational network. So we are continuously assimilating new observation system in the reanalysis. So this is the one changing thing in the reanalysis. Otherwise, we are freezing the data assimilation and the modeling system in the reanalysis. So we know the key strength, it is the gridded data set and consistency, all those things, but there are limitations also, so that we already discussed. But one of the limitation when we use the reanalysis product, especially the diagnostics for the renewable energy applications, we have to be careful. So we have to do some sort of bias correction or uncertainty removal before using the diagnostics variables in the renewable energy applications. So then why the renewable energy applications that we use the reanalysis data set? So for the renewable energy application, for planning the energy generation and the energy supply demand, all those things, we need a great large set of data. So the fundamental source of information to answer the questions of site mapping, variability, extremes and compensation effects are the that high quality data sets of renewable energy related variables. So if we see the reanalysis product, so reanalysis, it gives the long term, that is more than 3 decades, that gridded data set in a consistent way, and that exhibit the great potential in the field of renewable energy applications. So then what are the renewable energy applications of reanalysis? Here I just listed 2, but as we know, there are many applications in the renewable energy sector, that is the wave, tide, then the ocean heat potential, all those things are coming. So here I'm just listing only two. So these are the wind energy and the solar energy. So why that, where that applications are coming, the understanding the wind speed variability, we can use the reanalysis data set, estimating extreme wind power events, assessing wind resource patterns, and identifying the most powerful site for the wind energy farms. And coming to the solar energy, optimizing the solar energy generation, evaluating the solar radiation and solar resource assessment, modeling the solar photovoltaic, forecasting the photovoltaic module degradation. So there are a lot of a large number of applications if we see the reanalysis is concerned in the renewable energy sector. But the quality of the meteorological quantities in the reanalysis data set is important for its application. So we have to be cautious when we use these products in the reanalysis applications. So, sorry, I think this is an old version of my presentation. So can you please load the latest version? Sorry, so in this presentation, I have tried to incorporate almost all the reanalysis data set. As we know that almost all the reanalysis data set we use for the renewable energy sector. So, but to list a few that the main the data set that I just took the literature survey from different studies. So the ERA series, MERA series, and the JRA series. These are the some of the global reanalysis data set I have. The papers from the results from these that data set we used, I am putting in this particular presentation. And coming to the regional reanalysis data set, it is the COSMO regional reanalysis, then NAR, then BARA, IMDA. These are some of the reanalysis data set we used. But when we use the reanalysis data set, that as we are discussing, that we have to be careful when the products, when particularly when it is in the renewable energy sector. So we have to do some sort of bias correction, we have to do the uncertainty removal, and we need to see which reanalysis. So now if we have so many global reanalysis and the regional reanalysis also, so wherever we are having both global and the regional data set, so which one is the best for the renewable energy application, that also we need to do carefully. So then why do we need bias correction of reanalysis data set? So the bias correction is very important. So this is one particular study by Fluckfelder et al. 2024. So they used the ERA 5 data set and they found they have used approximately 23,000 wind turbines for Germany to assess the deviation between the simulated and measured energy in feed for 4 years. So the 23,000 wind turbine locations they have used, and what they found is in flat terrain, simulations based on reanalysis data overestimate measured results. And in topographically complex region, a minor overestimation and locationally an underestimation can be observed. So they did some sort of bias correction, the multilinear regression at turbine level. So, and what they found is, so this is the graph, this is the one of the figure I copied from this particular publication. So here if you see that the x-axis is the time step and y-axis is the capacity factor. So the blue one is the observation, and red line is the ERA 5 without bias correction, and the yellow line is the ERA 5 model with bias correction. So if you see that after bias correction, they can bring down the reanalysis closer to the observation. So the bias correction plays a vital role. So then how important it is to analyze the uncertainties in the reanalysis data for wind energy. So as we see that that we need to do the bias correction, that on the even on the flat terrain it is overestimating, sometimes underestimation. So the reanalysis can predict wind resource pattern over time, but reanalysis data is sufficiently reliable on offshore and flat onshore locations, but there are uncertainties greater on the mountainous and the coastal sites where wind speed and energy yield are significantly under and overestimated respectively. So we have to remove the uncertainty over this heterogeneous terrain like mountains and coastal site. So on this location, the use of high resolution regional products should be preferred over global data set, as they are better suited to resolve the detailed terrain features as well as, So thank you. So we have to do some sort of uncertainty removal. So there is a study from Gualtier 2022. They critically reviewed and updated the state of art of the uncertainties associated with the reanalysis dataset that directly used for wind resource assessment. So they used that 15 regional means reanalysis data set, that is 9 global and 6 regional reanalysis data set worldwide over 322 heterogeneous locations. So and they found that, sorry, it's not moving. So, yeah. So these are the data set they used in this particular study, Gualtieri et al. 2022. And this is the top figure shows the number of locations and the wind speed, the percentage share of wind speed calculation they used from different reanalysis data set, and the bottom figure, the pie chart shows the annual energy yield from different reanalysis. They used the raw data set without any bias correction, and after that they have done some bias correction, all those things. And after the bias correction, they have found that some the ERA 5 it contributes 46.8%, then MERA, then MERA 2, MERA, then some of the regional reanalysis also. So then we need to see which reanalysis is better for renewable energy applications, particularly the wind and solar. So if you see the global versus regional thing, so there are some lot of research published. The added value of high resolution regional reanalysis for wind power applications. So this is from Frank et al. 2020. So they have used four well-established wind towers in Europe for the reference of this purpose, and they used the global reanalysis and the regional reanalysis, the Cosmo regional reanalysis, and IRA interim and MERA 2. So the regional reanalysis performing significantly better, or at least similar to the global reanalysis over this four site. And the most extreme temporal wind changes at typical hub heights are unrepresented by global reanalysis between -80 and -43, while in the Cosmo regional reanalysis it represents with relative errors. It is less relative error, that is between -14 and +9%. So in this study, they are proposing that over those particular region, over the Europe, that the regional reanalysis, the Cosmo, it is performing better than the global reanalysis. And similarly, assessing the predictions of Australian offshore wind energy resources from reanalysis data set by Covin et al. 2023. So they have also used some of the observation site, and they assessed the wind speed distribution and accuracy and compared the predictions of offshore wind turbine power output in Australia from 3 reanalysis data set, that is BARA, IRA 5 and MERA 2. And they also found that the regional reanalysis is performing better than the global reanalysis, particularly for the wind energy, offshore wind energy applications. But significant variation was seen in prediction, and there was a lack of similarity with weather station measurements. So which highlights the need of more additional observation site-based measurements to verify the performance of regional or the global reanalysis data set. Then coming to the Indian region, so we have the Indian monsoon data simulation and analysis that we produced at NCMRWF in collaboration with UK Met Office. So this is the IMDA topography, and this is the IRA 5 topography. If you see, so IMDA is 12 kilometer resolution, and IRA 5 we are getting the product at 25 kilometer resolution. So the 12 kilometer resolution, that the topography is resolved, the highly resolved. And the bottom panel, it shows the IMDA climatology of with 100 meter wind, and this is the IRA 5 climatology. And the bottom rightmost figure, it is the wind energy production, the potential from the National Institute of Wind Energy, India. So if you see that here the terrain regions where we are having the Western Ghats and the gap in between, so there the IMDA is performing better. So the high resolution regional reanalysis, it is performing better over the Indian region also. So then we did some location specific analysis, which reanalysis is better. So we have selected some 4 different sites, and we use the 10 meter wind as such, whatever we are getting from the reanalysis from both IMDA and IRA, and we could not find a uniform result like that this particular reanalysis is performing better over this Indian region. So, but there are some studies by the wind energy group, that Meteodyne is a wind energy company based on France. So they have taken the IMDA data and they did some sort of post-processing of the IMDA data, IMDA and IRA, and they found that over the some of the locations over India, like one plain onshore location, and they derived the wind profile in the logarithmic wind profile in the lower atmosphere, and the monthly variation and the daily variation, and they found that the IMDA, the regional reanalysis, is performing better over the different sites that plain onshore. This is over a semi-complex inland region, and this is on an offshore region off the coast of Gujarat. So here they found that after doing some sort of post-processing, the reanalysis products become better for the renewable energy applications, particularly for wind. And they approached us and they want to use this data set for commercial use, and as per our policy that we are releasing the data freely for the research application, and we don't know what is the MOU or what is the terms and condition for the commercial applications of reanalysis data set, because they are not using the reanalysis data set as such. They are taking the reanalysis data set and they are deriving the secondary product, and the secondary product they want to commercialize. So maybe this community can formulate something how people can use the reanalysis product for commercial applications. So do we have to charge them or not? We don't know what to do. So they approached us for an MOU. So, but we were thinking that what to do. So this is the best forum to discuss those things. And this is the details of IMDA reanalysis. So we have around 40,000 registered users, and this is the domain. And this paper gives the details of IMDA. And so if we see the wind energy section, that IMDA, the regional reanalysis is, and the global reanalysis, they are performing well. But when we come to the solar, so this is again for IMDA. So this is the first figure that shows the IMDA climatology of the global horizontal irradiance, and the second one is from ERA 5. So what we found is in the regional, the diagnostics, the GHI, that it is there is an overestimation. And again, we compared the GHI over different locations over the Indian region. That, as you know, the India is a heterogeneous terrain region. We have hilly region, we have plain, so almost all the topography is available over the Indian landmass. So here what we found is we compared the IMDA and IRA5, and both the global and the regional reanalysis, they are not agreeing with the observation. So here also we need to do some sort of bias correction before using them in the renewable energy application. So one group from IIT Mumbai, they took the IMDA reanalysis data and they used the MERA2 data also, and they did some comparison. Also, these are the locations where they have the surface solar radiations over Indian region, and they did some comparison of the IMDA and IRA 5. So how it is how it is matching with the observation. And initially they found that there is lot of bias in the regional reanalysis compared to the global reanalysis, but they did some sort of bias correction, and what they found is after the bias correction, the 8-day that solar radiation the bias that is improved from 22.03 to 12.95 watt per meter square for the global reanalysis. But for the regional reanalysis, the bias was high initially, it was 31.95, and after the bias correction it reduced to 9.42 watt per meter square. So what we are seeing is in the regional reanalysis, whether it is IMDA or COSMO or BARA, that, or whatever the regional reanalysis, the biases are that systematic, and it is very easy to correct the bias. So after the bias correction, the regional reanalysis are more valuable product for the renewable energy application. But we don't have the regional reanalysis over all regions, so but we have to use the global reanalysis also. And in our studies, what we have seen after the bias correction, the biases in the global reanalysis, MERA, then ERA 5, all those, the biases are reducing drastically. So then bias correction, this is again over Europe, the bias correction of novel European reanalysis data set for solar energy application. So this is by Frank et al. So they again use the Cosmo reanalysis, which covers the European domain. And so then in this particular study, they have used the baseline surface radiation network GHI measurements from those baseline network as the reference. And what they found is that the shortcomings in the reanalysis and underestimation of GHI in the clear sky condition and overestimation of GHI in the cloudy conditions. So then they also applied the post-processing method based on orthogonal distance regression for two different regimes, that is the clear sky and cloudy sky. And after the post-processing, the post-processed GHI shows significant reduction in the systematic biases and improvement in representing the marginal distribution. So this is the results from that particular study, Frank et al. 2018 over Europe. So here we can see that they have used the observation, that is the baseline observations, and the reanalysis, regional reanalysis, then ERA interim and MERA 2. Here we can see that the MERA 2 is means matching with the observation, but the problem is MERA 2 is hourly data, but for the solar energy applications, they need the data at least in 15 minutes interval. So those type of products are not coming from the, not available from the global reanalysis, but the Cosmo reanalysis, they have the 15-minute product, but it is not matching with the, so if you see the red one, so the raw product, whatever the solar radiance from that, it is not matching with the observation. But if you see here, after the proper bias correction, so the red one is without bias correction and the blue is with bias correction, so it is matching closer to the observation. So we need some sort of bias correction before using all this data in the renewable energy applications, whether it is wind or the solar energy. So there is another study, geophysical constraints on the reliability of solar and wind power worldwide, by Tong et al. 2021. So in this particular study, they used 39 years of hourly reanalysis from MERA 2 and ERA 5 data. That is from 1980 to 2018, and analyzed the ability of solar and wind resources to meet electricity demand in 42 countries, varying the hypothetical scale and mix of renewable generation as well as energy storage capacity. So this is a huge the data set they have used, and they have studied for 42 countries. And assuming the perfect transmission and annual generation equal to annual demand but no energy storage, Tong et al. Found the most reliable and renewable electricity systems are wind heavy. And this study also helps to quantify the power, energy and utilization rates of additional energy storage, demand management or curtailment, as well as the benefits of regional aggregation. So these are some of the glimpses from this particular paper, this Tong et al. 2021. So they have studied for 42 countries from 1980 to 2018. And this is for these two panels. It shows one for the northern hemisphere and one for the southern hemisphere. So we have the top panel China, then Germany, US, and here in the right we have South Africa, Brazil and Australia. So the first one, it is the annual variability from 1980 to 2018. And the second one, it is the daily variability, summer, June, July, August months. And the third one, it is the daily variability, winter. So here if you can see that here the violet, this color, this is the wind, and yellow is the solar, and the red color, red curve is the energy demand. So if you see the annually, so that as they reported, the wind power is the reliable energy source. So here also, if you see the first the column, we can see the wind power the energies produced from wind. It is matching. It is almost matching with their energy demand throughout the period. And if you see the season wise, the summer or winter, so here we can see, as we see that we have the maximum sunshine hours during the daytime, so that is coming during this that during the summer, June, July, August. But here again we can see the wind power, there is a consistency in the wind power generation from those resources. And if you come to the winter season also, there is a variation in the solar energy, means incoming solar radiation, that sunshine periods. But the wind power, again, it is almost consistent if you see over this location. And coming to the southern hemisphere, here also we can see the wind power that is playing the most significant role, that is the consistent reliable energy we can use. So then this particular study, they already mentioned that, so the most reliable electricity and renewable electricity systems are the wind heavy. So for in future net zero emission energy system rely heavily on solar and wind resources. Spatial and temporal mismatches between resource availability and electricity demand may challenge the system reliability. So then the question is, so we have seen that we have a lot of the reanalysis data set, whether it is global or regional data set. Before using them into the renewable energy application, we may have to do some sort of bias correction, and after the bias correction, these products are the best one for the renewable application session. So then how can we improve the reanalysis for renewable energy application? So then we can increase the improve the reanalysis for the renewable application section. So first, enhance the observation network for renewable energy. So a regional and local network of surface observation, like automatic weather station, then upper air observing systems, along with data from remote sensing observations. So if you can increase the renewable energy related observations, then it can improve the reanalysis for particularly for the renewable energy application. Then meteorological observation from networks of toll towers and turbine anemometers. So as of now, the reanalysis, whatever the reanalysis data set we are producing, so we are not considering the turbine level observations. We are not assimilating those observations in the data assimilation system. So maybe in future, for considering the renewable energy applications, that is going to be the most useful in the coming years. So then we can consider how we can include those data, that is the turbine level measurements, that wind and temperature measurements, into the reanalysis data assimilation system. And ceilometer data that measures the thickness, ceiling and base height of cloud layers, these are very important. So we can, if we have the continuous data set from these type of instruments, we can see how much sunshine hours are there, how much energy we can produce from the solar energy resources. Those planning and all those things, this will help. And so including these observations in the like turbine level wind and the solar information, the cloud height, cloud thickness, and all those things in the data assimilation system may maybe then again we may have to use the rapid update high resolution regional NWP model. So we need the global reanalysis also, but at the same time the regional reanalysis, it is having more impact in the renewable energy applications. So then another one is improving farm scale prediction. So farm scale prediction, so we know the wind farms, so they maybe some acres of field we may be having. So can we do some sort of parameterization at farm level, so that the forecast or the reanalysis from those for those regions will be better. So yesterday we had the keynote presentation that they were telling the MERA 3. They are planning to assimilate the boundary layer height. So that is one sort of thing. So if we assimilate the boundary layer height in the reanalysis system, so it can give more better maybe the wind profile, the assimilation over the boundary layer, and it will be better for the wind energy applications. And how we can improve the wind forecasting over complex terrain, so we may have to use highly resolvable the topography data. So maybe we can think with how we can use for this we may have to go for high resolution reanalysis or the high resolution NWP, then only we can resolve the topography properly. So then the reanalysis, as of now, the reanalysis data sets are not developed with the awareness of renewable energy application. So whatever the reanalysis data set developed now, it is for weather related application or the climate, all those applications. So in future, when we plan the reanalysis, we may have to have communication with the we have to communicate with the renewable energy scientists and practitioners. So what they want from the renewable energy reanalysis community, so how they can use the reanalysis product to improve the renewable energy production. So this sort of communication that is very important when we plan the renewable reanalysis applications. Particularly, we cannot use the reanalysis product as such for the renewable energy application. So is it possible to give the wind power as a diagnostic product from the reanalysis, or the solar power generation as a diagnostic product from the reanalysis? So we are giving the 10-meter wind, 50-meter wind, 100-meter wind, but we are not giving what could be the wind power generation or the power generation capacity at this particular site. So if we can think about, we can give some sort of diagnostic variables like the power production from the reanalysis, that also will be useful for the renewable energy community. And see what are the challenges. So we know there are a lot of challenges. So forecasting wind and solar power generation is critical for grid stability and management. So it is very important. So if we have, if we forecast the wind accurately, so I think what I understood from our interaction with the wind energy producers, they need to give a forecast that this much power they will be generating and they will be transferring this much power to the grid. So if they're producing less and if they're producing more, if they're producing less, they are losing something, and if they're producing more, then also they are losing something, because the more energy they cannot transfer to the grid. So that is going to be waste. So there should be some optimal thing. So whatever they are proposing, that whatever they are forecasting, so this much power, this particular from this particular wind energy company, we are transferring to the grid. So that is very important. So the accurate forecast of wind and solar irradiance, that is very much important. And as we discussed, that wind and solar form variable resources and strongly connected with varying weather at all scales, and the reanalysis data set generally feature uncertainties at those scales. So, so we have to see how we can, so whether it is high resolution reanalysis, or it is through data assimilation or through the parameterization or explicit things that we need to see. These are some of the challenges. So then we know the geographical diversity of renewable energy rich region. So that is from coastal areas to the deserts and mountains, so requires different approaches. So the same approach will not work for all these geographically diverse renewable energy rich regions. So the bias, whether it is the bias correction, uncertainty removal, so we have to apply different bias correction techniques over different terrain. So that is also a challenge. So then the current reanalysis data sets are not adequate to support the renewable energy industry requirement in terms of the weather variables, whatever the weather variables it is coming from the 10-meter wind, 50-meter wind, like that. But if you see the turbines, it is at a different height, that it may be 80, 150, 200 meters height. So what they are doing, they are taking the data and they are doing some sort of, they are using some sort of techniques and interpolating the data to the turbine height. So there also some, means it is the secondary processing, there also they are introducing some sort of error. So the reanalysis itself, if they can give the output at the turbine level, then it would be good. And number of revisions per day. So as we see that almost all the global reanalysis and majority of the regional reanalysis, it is the 6-hourly or 12-hourly assimilation cycle. So whatever we are getting, the analysis may be maximum four times in a day, and after that it is the hourly forecast from the that the short forecast. So they may need more number of revisions per day. So is that possible from the reanalysis community? And another one is the time granularity. So time granularity is very important. So we have the hourly product, we have 3 hourly product, 6 hourly product, daily, seasonal. But for this wind energy applications, we need a minimum temporal resolution of 15 minutes. So is that possible from the reanalysis community to generate the products, especially the wind and solar energy related product at a temporal resolution of 15 minutes? So that is also a challenge. And quality of diagnostic variables like hydrological product and the GHA, etc. So that we have to be very cautious when using in the renewable energy application. So which will do that better, whether it is DA or the better parameterization. So these are some of the challenges that reanalysis community has to take up and discuss. And maybe for in the future reanalysis production, we may have to, if not all, some of the things we can try to address. I'm not sure. So I will stop here.